So we will discuss about Hall effect, very important, and this has great significance. Hall is the scientist name, and he discovered some effect that we are talking as Hall effect. Okay. So before we do the statement and also the derivation, the importance we need to know why Hall effect is important. Remember, to know the number of carriers either in the valency band or in the conduction band, we had 2 pages of derivation, right? Very burden. So it involves lot of parameters. So if I suddenly ask, look, I have heated the samples. So far you have done the Fermi level problems. I am asking what is the probability that electron can go. My next question would be, okay, you are sure that some 0.2 probability is there. How many electrons are going? If I ask you that, I have supplied this much temperature, heated the sample to some 300 Kelvin. Now I want to know exactly how many number of electrons are there, or else what is the charge carriers. It can be either electron or it can be either holes. Some charge carriers is how many number of electrons. If it is electron in the conduction band, if it is holes, how many number of holes are there in the valence band. So to know that the carrier concentration, it was burdensome always to you have to know different parameters, just like in the derivation, then you need to substitute there, then get the number, and it is very tedious. But using the Hall effect, if you know typical parameters, very little parameters, which is very easy to extract, that you will appreciate at the end of this, you can easily know how many number of electrons are there. If electrons, how many number of holes are there if it is holes. It is very easy. Point number one. Point number two, so what is the importance we are talking, importance of Hall effect. Before I actually teach what is Hall effect, the importance is, point number one, you can know to know the carrier density. Okay. Carrier density easily, which means n, I am talking about n. What is the number of either electron or hole? Point number two, I will give you some semiconductor. I will not tell whether p type or n type, some unknown, and you want to know whether it is a p type or not. What are the carrier concentration? Is it valency? I mean, is it electron or hole? So by using the Hall effect, it is easy to know the type of semiconductor. Do small Hall effect experiment. We actually have that in the teaching lab also. So this is again we will teach in the laboratory course. Okay, it will be kind of revision. Maybe after IA you will be doing. We will be performing this experiment. You will be knowing what is the type of semiconductor. At the end, you will actually tell whether it is N type or P type. And also, it can be used as a sensor, that is called Hall sensor. What Hall sensor will give you is, it will measure the field, magnetic field. Okay, to measure magnetic field at any instrument. You are doing MRI scanning somewhere, suppose in the health sector, you want to know how exactly how much field is produced. Using the Hall sensor, you can know easily. Or else any sensitive electronic equipment where magnetic field is involved, you have to use it. All the speakers or our mobile phones, aircrafts, everywhere magnetic field is involved. Okay. How do we produce? Speakers means you are using permanent magnet, but otherwise we use the current to produce the magnetic. So if we are using current to produce the magnetic field, just like in the MRI case, how much current I need to give? It cannot be infinite. If you are giving more magnetic field, that is also dangerous. So we will be using Hall sensor. We put a sensor, increase the current, then it will detect what is the magnetic field. So this is minimum things that you need to know before you go to the Hall effect. This is the importance of Hall effect. So now let us go back and look the statement of the Hall effect. So what is the Hall effect statement? So statement, then the derivation. Okay. Let us look at the statement. Very easy statement. Take a current carrying conductor. First understand, then you write in your own thing. Nothing to write, don't write anything. Try to understand. Then you put in your own words. Suppose I take some semiconductors. This is my semiconductor carrying current in certain direction. Okay. So suppose it is carrying current in this direction. Current is I. Some direction. Call it as x axis. So the statement starts like this: any current carrying semiconductor, not over, in specific direction. Now I did keep this current carrying semiconductor in the magnetic field perpendicular to the current direction. That is called transverse magnetic field. So any current carrying conductor experiences transverse magnetic field. That is the meaning. Or else put it very lightly in your own words. Any current carrying conductor carries current in x direction, and if you apply magnetic field in z direction or else y direction, because all are perpendicular to each other. So current is going in x, you apply either in z or y, no issues. Or else simply you call, if it experiences a transverse magnetic field, what happens? What happens is a electric field is produced in opposite to x and z directions, or else opposite to the current and field directions. What is the direction? Current is in x direction, field is in z direction, opposite to that is y only, right? So a field is produced in y direction. This is the y direction. Okay. Or else for easiness, suppose this is z direction, bz. Suppose that is z direction. X, z, then field will be produced y direction. Okay. So for easiness to understand, z, this means z is this way, x is this way, z is coming out of the board direction, then field will be y. Okay. Current is going in this direction and you applied a magnetic field exactly perpendicular direction, then both field direction and current direction, both another perpendicular direction is there, that is y direction. The field will be produced in the y direction, that is called Ey. So the directions are very very important. This is a simple statement, you can put it in your own word. I am not saying you have to by heart like that only, but read, try to understand, you can keep it in your own word, but without compromising these directions. This is simple statement. Now we will ask, define Hall effect. Define means statement. This is the statement. Give a beautiful diagram. We'll draw the diagram again one more time. And derive, you said no, how voltage is, you are getting the voltage. This is discovered by Hall. So we say that this voltage is nothing but Hall voltage. So derive expression for a Hall voltage, that we will ask. And from this Hall voltage we also get Hall coefficient. So derive expression for a Hall voltage and Hall coefficient. That is how the question will be, right? Define Hall effect, derive expression for Hall voltage. So now we will derive the expression. Okay. Expression is very easy because you understood already about the diagram. 90% work is with the diagram only. Okay. So derivation. After this, let us go back to derivation. Sometimes we also ask you theory. You cannot directly jump into the derivation, no? You explain the process, how it is happening. So we'll explain, then we'll do the derivation. So theory is very simple. A diagram. Let me draw the diagram. Actually, tools are there in this board, but I am using my hand only. Just to make it look like a 3D one. This is some semiconductor we are taking. Unknown semiconductor. Let us take. Now, what is the statement says? Condition number 1 is take any semiconductor and it should carry the current. Okay. So theory is same thing. Take a semiconductor, and when you say semiconductor, dimension should be there, some dimensions. So you can say that length is L, width is D. Okay. Or you can calculate area, you can calculate volume. All these are mandatory things for any semiconductor, that we know, because you are only taking it. Now let us apply current, or else it is current carrying current in x directions. So I call it is the x. Very, very important directions. So let us fix x in this direction. So it is carrying current in this direction, I x. Simple. So current means what? Flow of charges. So I say current is going in this. Basically, what is happening? Charges are moving from one place to the other place. Okay. If I connect my wire this side to the battery, charge moving from this end to that end, to the light side, battery to the light side. So now I say the current is going in this direction. So charge was here, it started moving from here to that side. Yes, no? So charge is going, happily it is moving and going like this. Its same is it wants to come like this. Now it is not free. What you did? You applied magnetic field. Applied magnetic field will be denoted with B in Z direction. If the charge is free, it has a freedom. Current is going means you already dictated charge has to move in this direction. That is what Lorentz force, no? What is Lorentz force? F is equal to EQ. Forgot, on a charge due to the application of the electric field. The force will be, the charge will experience a Lorentz force. If it is only electric field, that is F is equal to EQ in a particular direction. Okay. So charge wants to go in this particular direction, but you applied the field, but this field also now try to influence the charge. Hello, the charge sees the field now. How the field influences? Again +2, you remember, a test charge is there. Throw the test charge in the magnetic field, what happens to the charge? Remember? Correct, huh? Rotates, circular motion. Recollect. Okay. Circular motion it tries to go. So due to the application of magnetic field in Z direction, let us take this as Z direction, B, Z. Now this test charge wants to go this direction, but field says, hello, you cannot go that direction. Field wants circular motion. Circular motion. That's what cyclotron, no? Cyclotron means what? You apply magnetic field, it moves in the circular motion. So whenever you apply magnetic field on the test charge, circular motion will come. Due to the force is like that, curl force we will be writing that force in the derivation. But whereas this current wants in the straight path. Now charge has to decide which way to follow. Which way? What do you advise? Which way to follow? Can the charge should go like this because current is dictating, or else it should see the field and it should come as a circular motion? Which way? There are competitive forces are there. When two competitive forces are there, where it will go? Suppose I am standing here, one person is pulling that side, other one is pulling this side. Which way I should go? Correct. Whatever is more force, in that direction I will go. Suppose equal forces are there, I will be here, right? No, that condition will apply. So it cannot go straight. It may go straight if it is. Why it is going? It may go straight if it is only the electric field. Symbols I am not using, no. This one. It may go circular if it is only the magnetic field, but if both the forces are equal, that I say as a equilibrium, it wants to go like this, but it also takes a sort of circular, not circular. This, what is this? Curved path. It may take a curved path, and instead of reaching this place, other end, from A to B it cannot go. Instead of going from A to B, it reaches the sides. So the electron comes and settles here. Now another electron wants to go, it cannot go, it again comes and settles here. All the electrons comes and settles here. So this side of the plate is completely become with charge? All negative, because it is electron. Because this is negative, negative cannot be alone, no? It will induce the positive on the opposite side. Yes sir. So basically what is created? When the electric force and the magnetic force are equal, that is the condition. When both are equal, we have developed an electric field. What is the direction of electric field here? Look, from where to where? This is the direction of the electric field. So that is called E. What is the direction? I is in X, B is in Z. Here what is this direction? E, Y. This is the theory part. You have to explain the same thing. Okay. What is the key point here? Due to the electrical force, charge wants to straight path. Due to the magnetic force, it wants circular path. But when there is an equilibrium between those two, it takes a curved path and the charges goes and settled on the Y plate. Therefore, a potential is generated on the sides or else in the Y direction, which is opposite to both the current and also the field direction. Opposite means no, transverse, perpendicular. Use the perpendicular term, not the opposite. Okay. So now all these three terms are opposite to each other. That is the key. Actually, the directions are very, very important. This is simple theory. Understood, no? Once theory is there, derivation is very, very easy. We'll do the derivation now. Let us do the derivation. So the diagram you have to remember. So voltage is generated at equilibrium. So let us start with the equilibrium. Derivation is very straightforward. At equilibrium, what are the two forces that are equal? At equilibrium, electrical force is equal to the magnetic force. So let us write electric force is equal to magnetic force. So that is the equilibrium condition. Now what is the electrical force? F of E, let me write. Magnetic force F of B. Go to +2 knowledge. Tell me, we know that. What is the electric force? Electric force is nothing but F of E is nothing but, if charge is Q, some textbooks they may use E, anything. If charge is Q, F of E is nothing but Q into E. What is the direction of E? XYZ. Y. According to our diagram. Somebody can put X, no problem. But make sure all three are perpendicular to each other. According to our diagram, it is Y. Right? Now let us write magnetic field also. Let us write magnetic force. Magnetic force F of B. This is also, you know that. Okay, we know that. So who knows it? Magnetic force F of B. Who knows the equation? Collect +2. Q into QVB. Correct only. Or else imprecise, if I want to talk about Q into V cross B, curl will come. That's why it rotates like this. Okay. For simplicity, Q into V into B direction Z. What is V here? V, not B. V. Q V B. Q is charge and this is magnetic field. What is this in between? Potential difference, huh?